Section 1.5, Dispersion. Learning objectives. By the end of this section, you will be able to 1. Explain the cause of dispersion in a prism. 2. Describe the effects of dispersion in producing rainbows. 3. Summarize the advantages and disadvantages of dispersion. Everyone enjoys the spectacle of a rainbow glimmering against a dark, stormy sky. How does sunlight falling on clear drops of rain get broken into the rainbow of colors we see? The same process causes white light to be broken into colors by a clear glass prism or a diamond. Figure 1.20. Figure 1.20. The colors of the rainbow A and those produced by a prism B are identical. Credit A. Modification of work by Alfredo 55, Wikimedia Commons. Credit B. Modification of work by NASA. We see about 6 colors in a rainbow: red, orange, yellow, green, blue, and violet. Sometimes indigo is listed, too. These colors are associated with different wavelengths of light, as shown in Figure 1.21. When our eye receives pure wavelength light, we tend to see only one of the 6 colors, depending on wavelength. The thousands of other hues we can sense in other situations are our eye's response to various mixtures of wavelengths. White light, in particular, is a fairly uniform mixture of all visible wavelengths. Sunlight, considered to be white, actually appears to be a bit yellow, because of its mixture of wavelengths, but it does contain all visible wavelengths. The sequence of colors in rainbows is the same sequence as the colors shown in the figure. This implies that white light is spread out in a rainbow according to wavelength. Dispersion is defined as the spreading of white light into its full spectrum of wavelengths. More technically, dispersion occurs whenever the propagation of light depends on wavelength. Figure 1.21. Lambda, nm. Infrared. 800. Visible light. Red. 700. Orange. Yellow. 600. Green. 500. Blue. Violet. 400. Ultraviolet. 300. Figure 1.21. Even though rainbows are associated with 6 colors, the rainbow is a continuous distribution of colors according to wavelengths. Any type of wave can exhibit dispersion. For example, sound waves, all types of electromagnetic waves, and water waves can be dispersed according to wavelength. Dispersion may require special circumstances and can result in spectacular displays such as in the production of a rainbow. This is also true for sound, since all frequencies ordinarily travel at the same speed. If you listen to sound through a long tube, such as a vacuum cleaner hose, you can easily hear it dispersed by interaction with the tube. Dispersion, in fact, can reveal a great deal about what the wave has encountered that disperses its wavelengths. The dispersion of electromagnetic radiation from outer space, for example, has revealed much about what exists between the stars, the so-called interstellar medium. Nick Moore's video. https://openstaxcollege.org/L721 Nick Moore vid closing parenthesis. Discusses dispersion of a pulse as he taps a long spring. Follow his explanation as Moore replays the high-speed footage showing high-frequency waves outrunning the lower-frequency waves. Refraction is responsible for dispersion in rainbows and many other situations. The angle of refraction depends on the index of refraction, as we know from Snell's law. We know that the index of refraction, n, depends on the medium. But for a given medium, n also depends on wavelength, Table 1.2. Note that for a given medium, n increases as wavelength decreases, and is greatest for violet light. Thus, violet light is bent more than red light, as shown for a prism in Figure 1.22b. White light is dispersed into the same sequence of wavelengths as seen in Figure 1.20 and Figure 1.21. Table 1.2. Medium. Red, 660 nm. Orange, 610 nm. Yellow, 580 nm. Green, 550 nm. Blue, 470 nm. Violet, 410 nm. 1. Water. Red, 1.331. Orange, 1.332. Yellow, 1.333. Green, 1.335. Blue, 1.338. Violet, 1.342. 2. Diamond. Red, 2.41. Orange, 2.415. Yellow, 2.417. Green, 2.426. Blue, 2.444. Violet, 2.458. 3. Glass, crown. Red, 1.512. Orange, 1.514. Yellow, 1.518. Green, 1.519. Blue, 1.524. Violet, 1.53. 4. Glass, flint. Red, 1.662. Orange, 1.665. Yellow, 1.667. Green, 1.674. Blue, 1.684. Violet, 1.698. 5. Polystyrene. Red, 1.488. Orange, 1.49. Yellow, 1.492. Green, 1.493. Blue, 1.499. Violet, 1.506. 6. Quartz, fused. Red, 1.455. Orange, 1.456. Yellow, 1.458. Green, 1.459. Blue, 1.462. Violet, 1.468. Table 1.2. Index of refraction, N, in selected media at various wavelengths. Figure 1.22. A. Pure lambda. Incident light. Glass prism. B. Incident white light. Glass prism. Red, 760 nm. Violet, 380 nm. Figure 1.22. A. A pure wavelength of light falls onto a prism and is refracted at both surfaces. B. White light is dispersed by the prism, shown exaggerated. Since the index of refraction varies with wavelength, the angles of refraction vary with wavelength. A sequence of red to violet is produced, because the index of refraction increases steadily with decreasing wavelength. Example 1.5. Dispersion of white light by flint glass. A beam of white light goes from air into flint glass at an incidence angle of 43.2 degrees. What is the angle between the red, 660 nm, and violet, 410 nm, parts of the refracted light? Figure. Air. Theta air. Flint glass. Theta red. Theta violet. Strategy. Values for the indices of refraction for flint glass at various wavelengths are listed in Table 1.2. Use these values for calculate the angle of refraction for each color and then take the difference to find the dispersion angle. Solution. Applying the law of refraction for the red part of the beam. N air, sine theta air, equals N red, sine theta red. We can solve for the angle of refraction as theta red equals arc sine, open parenthesis, N air, sine theta air, divided by N red equals arc sine, open bracket, 1.000, sine 43.2 degree, divided by 1.662, closed bracket, equals 27.0 degree. Similarly, the angle of incidence for the violet part of the beam is theta violet equals arc sine, open parenthesis, N air, sine theta air, divided by N violet equals arc sine, open bracket, 1.000, sine 43.2 degree, divided by 1.698, closed bracket, equals 26.4 degree. The difference between these two angles is theta red minus theta violet equals 27.0 degree minus 26.4 degree equals 0.6 degree. Significance. Although 0.6 degree may seem like a negligibly small angle, if this beam is allowed to propagate a long enough distance, the dispersion of colors becomes quite noticeable. 1.4. Check your understanding. In the preceding example, how much distance inside the block of flint glass would the red and the violet rays have to progress before they are separated by 1.0 millimeter? Rainbows are produced by a combination of refraction and reflection. You may have noticed that you see a rainbow only when you look away from the sun. Light enters a drop of water and is reflected from the back of the drop, figure 1.23. The light is refracted both as it enters and as it leaves the drop. Since the index of refraction of water varies with wavelength, the light is dispersed, and a rainbow is observed, figure 1.24a. No dispersion occurs at the back surface, because the law of reflection does not depend on wavelength. The actual rainbow of colors seen by an observer depends on the myriad rays being refracted and reflected toward the observer's eyes from numerous drops of water. The effect is most spectacular when the background is dark, as in stormy weather, but can also be observed in waterfalls and lawn sprinklers. The arc of a rainbow comes from the need to be looking at a specific angle relative to the direction of the sun, as illustrated in Part B. If two reflections of light occur within the water drop, another secondary rainbow is produced. This rare event produces an arc that lies above the primary rainbow arc, as in Part Circa, and produces colors in the reverse order of the primary rainbow, with red at the lowest angle and violet at the largest angle. Figure 1.23. Water droplet. Sunlight. Refraction. Reflection. Red. Violet. Figure 1.23. A ray of light falling on this water drop enters and is reflected from the back of the drop. This light is refracted and dispersed both as it enters and as it leaves the drop. Figure 1.24. A. Violet. Red. Theta. Figure 1.24. A. Different colors emerge in different directions, and so you must look at different locations to see the various colors of a rainbow. B. The arc of a rainbow results from the fact that a line between the observer and any point on the arc must make the correct angle with the parallel rays of sunlight for the observer to receive the refracted rays. C. Double rainbow. Credit C. Modification of work by Nicholas, Wikimedia Commons. Dispersion may produce beautiful rainbows, but it can cause problems in optical systems. White light used to transmit messages in a fiber is dispersed, spreading out in time and eventually overlapping with other messages. Since a laser produces a nearly pure wavelength, its light experiences little dispersion, an advantage over white light for transmission of information. In contrast, dispersion of electromagnetic waves coming to us from outer space can be used to determine the amount of matter they pass through.